This is exam 1 review, and we start with number 1, which says find the equation of the line that is perpendicular 4x plus 2y equal negative 4 and passes through the point 2 comma 4. Okay, so we begin with solving this equation, and we get 2y equals negative 4 minus 4x. Divide both sides by 2, so we get y equals negative 2 minus 2x. And so we see the slope of this line is m equals negative 2. It's just the coefficient in front of the x term. And if we want to find the slope of the other line, we need slope and point. And so the slope of this other line, called m perpendicular, is equal to, and it gives you a hint here, negative the reciprocal of the slope that gives the slope of the perpendicular line. Alright, so all that means is just take this number here and take negative the reciprocal. So negative the reciprocal, so 1 over negative 2, which equals 1/2. So there's the slope, and they give us the point, 2 comma 4. And once I have slope point, I can use slope point form, so y minus y1 equals m times x minus x1. And I simply plug in. So y minus 4 is equal to 1/2 times x minus 2. And I can solve this then for y, so y minus 4 is equal to 1/2 x multiplied through by the 1/2. 1/2 times negative 2 is a negative 1. And I simply add 4 to both sides, and I get y equals 1/2 x. If you add 4 to both sides, then I get plus 3. And so this is my answer. Now we can see here that the slope is 1/2, which is negative the reciprocal of negative 2, and if you plug in 2, and for x, you do see you get out 4. The next question talks about explaining these various things like completing the square, the equation of a circle, and so on. So let's talk a little bit about completing a square, and we'll involve the equation of a circle with it. So first, for the equation of a circle, what do we have? So it's x minus h quantity squared plus y minus k quantity squared is equal to r squared. And of course the center is given by h comma k, and the radius is equal to, of course, r and the above formula. So let's just come up with a real quick example, and this is probably not going to be very neat because I'm making it up. So let's do x squared plus 4x plus y squared minus, let's do 2y plus 7 equals, and then let's do what? Let's do 29. Let's see what happens here. Okay, so the idea of completing a square, so we'll involve this here too. What I want to do is I want to make this thing here look like something x minus something squared plus y minus something squared equal to something else squared. And so the completing the square, the idea is you can make this into x plus or minus something squared by following the rule, add half the middle term squared. So you add half the middle term squared. And so if you follow this rule, what we can do is we have x squared plus 4x, and then half the middle term would be 2, and if we square it, it's 4, and if we add 4, we better take off 4 right next to it. And then over here, we have y plus y squared minus 2y, and half its middle term is negative 1, squared is positive 1, so plus 1. Make sure you subtract off 1 right next to it, or you'll change the equation. Plus 7 is equal to 29. And so what I get here, if you think about it, is I have these terms here, which I can collect together, and I have these terms here, which I collect together. And because of the saying, add half the middle term squared, what should happen is that this should be x plus 2 quantity squared. All right, so that's what's in green there. And then minus 4 plus, and then this turns out to be y instead of plus, it's minus because it's minus 2y, minus 1 quantity squared, and then I have minus 1 plus 7 is equal to 29. Great. All right, so let's bring the numbers together. So I have x plus 2 quantity squared, and then I have plus y minus 1 quantity squared. I have minus 1, minus 4, minus 1, which is a negative 5, plus 7, so plus 2 is equal to 29. And actually, I'm going to change this right-hand side so we can make this nice. So instead of having it equal to 29, let's just change it. And let's make it equal to, instead, 27. And you'll see here in a minute, then you'll get a nice looking radius. All right, so I subtract 2 from both sides, and you can see I'm going to get x plus 2 quantity squared plus y minus 1 quantity squared equal to 25. And so the center of my circle is given by, so my center is given by negative 2, comma 1. Right, negative because it's x minus a negative 2, and then 1 because it's y minus k, so k is 1. And then my radius, of course, this is r squared right here at 25, so r is equal to 5. And I could even draw this if I really wanted to. I go over 2, 1, 2, up 1. So here's my center at negative 2, comma 1. And I just draw a circle the best I can. And of course, the radius here, r, let's just say, r is equal to 5. And so that's the idea. All right, so that's completing the square and the circle. These are out of the way. Let's talk about a function, domain. Let's talk about all these. A function, domain, increasing, decreasing, local max, local min, concave up, concave down. And then finally, we can do these inflection points. Okay, so the idea of a function. Most familiar type of function, we use this functional notation, f of x equal to some formula, say x. The idea is you put something in, then you get something out. You can make this a bit more sophisticated by saying that a function is simply a rule that assigns to each element of the domain one member in the range. The crux of the matter is that if you put something in, you only get one thing out. A function can't go to two things. And so a function has a domain and a range. In general, there are three things that are going to limit our domain when we're working with formulas. So 1, you can't divide by 0. 2, if you have a square root or any even root, you have to make sure it's bigger than or equal to 0 underneath there. Otherwise, we have to deal with complex numbers. And then 3, if you're dealing with logarithmic functions or just the ln, it always has to be bigger than 0 on the inside. The range are the possible outputs. So for example, f of x equal to x squared. Nothing limits my domain because I don't have a denominator, I don't have any square roots, and I don't have any natural logs. So what I can say is that my domain is equal to all real numbers, so from minus infinity to infinity. So that's all the possible inputs. Whereas my range is going to be different because I'm squaring things. And if I'm squaring things, it's always going to be 0 or positive. So my range is actually going to go from 0 to infinity. And I can't have any negative numbers because you can't square a real number and get a negative. If you square a real number, it's always a 0 or positive. And there are several other examples you can come up with formulas. Just remember domain, all possible inputs, range, all possible outputs. The next thing, how do functions change? Okay, so functions can increase, so they can go up, right, or they can go down. So they can either increase or they can decrease. If they increase and then decrease, we get what's called a local maximum. So let's call this a max. If they decrease and then increase, we get what's called a local minimum. These are also called concave down, because it's part of a frown, versus this one, which is called concave up, right, which is part of a smile. Inflection points happen when we have a change in concavity. So if you go concave down to concave up, there's some point in between here that has no concavity, and we call this point the inflection point. Concavity is relatively important to our society. If you think about it, we like to track lots of numbers like unemployment, and if unemployment's going up, it's going from here to here, there are a number of ways it can go up. It can go up like this, it can go up like this, or it could go up at sort of a constant rate, so that's supposed to be a line like that. So in general, there's sort of three ways it can go up. Now, going up on this bottom, if it's unemployment over time, this is a very bad thing. Right? It says the unemployment rate is actually accelerating. Right? Whereas this on the top, I know it's going up, so yes, that's bad, but it's actually good because maybe it'll level off and eventually start to come down. And then this one from here to here is going up at a constant rate. The next thing we want to talk about, let's see here, are the inverse functions, even functions, elementary functions, and odd functions. So let's talk about all these kind of ones, because they kind of go together. So let's talk about these right here. All right, so once we have this basic understanding of functions, you put something in, you put something out, we come to this idea of elementary functions. And it's a very simple idea. It basically says most of the functions that we work with, or you have worked up to now, are built out of some very basic functions. One, you have what are called the power functions. Two, you have what are called the exponential functions. I guess we should write these down. So a power function looks like this. F of x is equal to x to a power, so x to the n. N can be any real number. It can be positive, it can be negative. We'll even let it be 0. And we'll also include the constant functions in here, so like 2, 3, 4, or any real number. The exponential functions, all we really need is f of x equal to e to the x. And 3, we have logarithmic functions. And it turns out all we really need for this one is the natural log function, so f of x equal to ln of x. And then number 4, we have the trigonometric functions. All right, so these involve, let's see, we have the cosine of x, the sine of x, the tan of x, right, which is really just the sine of x divided by the cosine of x. And then we have their partners over here. We have the secant of x, which remember is just 1 over the cosine of x. The cosecant of x, which is equal to 1 over sine of x. And then cotan of x, which is just 1 over tan x. So it's cosine x over sine x. So really there's just 2 trigonometric functions in some sense, cosine x and sine x. And this is what we kind of mean by the elementary functions. And all the other functions we work with can be built out of these functions by adding them, subtracting them, multiplying them, dividing them, and finally composing them. And we have a problem later where we use this composition, which is usually what students get kind of stuck on. Other types of functions we care about, there are inverse functions. So let's talk a little bit about inverse functions. The notion of an inverse function, the idea is I have a function that takes me one way. So I could have, like, let's say f of x equals, the standard example might be like e to the x. And so if I have a number here 2, it'll take 2 over here. You plug 2 into the e function, you get e squared. And you would like to have a function that takes you back to 2. And we typically call this function f inverse of x. And it turns out f inverse of x in this case is ln of x. That's one way you can define ln of x. Right? ln of x is a number that if you raise e to it, you get back what's inside here. You get back x. And so it's inverse, right? Ex takes me one way, ln takes me back. Now, of course, there's simpler examples other than this one. You could do something real simple, like instead of f of x e to the x, take it x plus 2. All right, then it'll take 2 to 4, and then f inverse, of course, would be instead of plus 2, you do the opposite, minus 2, and it'll take 4 back to 2. But that's the idea of an inverse function. We also have these even and odd functions. So let's talk a little bit about what we mean by even functions and odd functions. So an even function, the idea is if you plug in negative x, you just get back the same thing if you had f of x. Right, so it's sort of like a football field, a goalpost on a football field. I always think, here's the standard sort of example of an even function, y equals x squared. For an odd function, you have a similar idea. You have f of negative x, but instead of positive, you put a negative sign here, and this is equal to f of x. And so instead of a goalpost, you have one going one way and the other going the opposite way. So this is y equals x cubed, which is a standard example of a odd function. Now we can do all kinds of things with these, like we can make up a function like f of x equals, let's say, absolute value of x divided by x. And we can ask this question, is it even or odd? Or is it neither? It could be, most functions are neither even or odd. And the way we do this is we test it. So you can plug in f of negative x and see what happens. So f of negative x is equal to absolute value of negative x over a minus x. And then that's equal to, of course, absolute value of x. You can ignore the negative sign because absolute value makes it positive over negative x. And you see that that's not equal to the original f of x. So we know it's not even. Okay. Now, it turns out that it's actually odd. And you can see that if you put a minus sign here, then you put a minus sign here, and then a minus makes this a plus, and now it is equal to. All right, so now we can do away with that not equals, and we do get it to be equal to f of x. So it's not even, but it is odd. So f of x is odd. The next thing we want to look at are these trig identities. So let's talk a little bit about them. So for trig identities, the one that I always remember, cosine squared x plus sine squared x is equal to 1. If you choose one of these, either sine squared or cosine squared, and divide by it, so let's take like cosine squared x, divide both sides by cosine squared x, I get 1 plus tan squared x equals 1 over cosine squared x, which is secant squared x. If you divide by the other one, you get cotan squared x plus 1 is equal to cosecant squared x. So these are the standard first three identities. We also have the double angle identities. So sine of 2x is equal to 2 sine x cosine x, and cosine of 2x is equal to 2 cosine squared x minus 1. So these are called the double angle identities. And there's also these half angle identities. So we have sine squared of x and cosine squared of x. And they basically look the same. The only difference is you have a plus for this one. So cosine of 2x, all divided by 2. And instead of plus, for sine squared x, you get a minus. And like I said, these will come in handy later when we're doing integration. So those are the basic identities you're expected to know. And then finally, let's talk about the Pythagorean Theorem and similar triangles. So remember the Pythagorean Theorem, it's valid for right triangles. And so we have side A, B, and C. And it just says a squared plus b squared is equal to c squared. So we're going to use this theorem a lot later on in various word problems. And the same goes for the law of similar triangles, which says basically if you have two triangles, so here's one triangle. Let's make it real big here. And then I have another triangle inside it. It doesn't have to be a right triangle, so let's just do away with that idea real fast. Let's just make it so it's clear. It does not have to be always a right triangle. So it could be any old triangle. And then you have another triangle inside it that's similar, so a triangle like this. And let's label this little a, little b, little c. And then in red, the red triangle, we'll label big A, this side big A, big B, and then big C. We know that these ratios are the same. So if you take little a, let's say, to little b, it should be equal to big A over big B. And they hold for every single one of these. Right? So if you match up the sides and take the ratios, those should be the same. We move on to number 3, which we want to find the domain of this function here. And we remember again the domain, if we're given a formula, there are only 3 things that are going to limit our domain. And this follows because of these elementary functions. There are only 4 elementary functions, and the first one we know we can't divide by 0. And the second one, if we take square roots, we need to make sure they're bigger than or equal to 0. And the third one, if we have ln functions, we have to make sure it's bigger than 0 on the inside. And so we do have a denominator. So let's switch pens here. So here's my denominator. So I need to make sure x is not equal to 0. And there's no other denominator, so that's done. And then I do have a square root, so I need to make sure x plus 1 is bigger than or equal to 0. And so this tells me x is bigger than or equal to -1. So I have 2 restraints on my domain. X can't be 0, and x has to be bigger than or equal to -1. Now I don't have any ln's, right? So those are all done. If you need to, you can make a number line. And the number line would say there's a hole at 0, because x can't be 0. And then at -1, it's everything that's bigger than it, so everything to the left. So this is all the stuff in my domain. And so I can say d is equal to include -1 to 0, don't include 0, union, don't include 0, to infinity. Now to find the range, it's a little bit harder. So if you wanted to find the range of this function, you'd have to graph it. This is not a function I would give you because I don't think its graph probably looks that great. Okay, on this one, now I want to talk about the algebra function. So I've talked a little bit about this before when we talked about the elementary functions. So the idea is that you can add, subtract, multiply, and divide to create new functions. You can also put them together in pieces. Right? So you get piecewise defined functions. And you can also, then the fifth operation here is composition, which we're doing here and here. So let's do part A first. If we want to do f of g of x, that's actually equal to, well, wherever I see a g, I'll replace it with what it's equal to. So f of the square root of x plus 2. And then that's equal to, remember, f is just a rule. It says whatever's here, whatever's right here, I put right here. And I square it and take away 1. So whatever's here, I square it and take away 1. So square it, and I get x plus 2, because the square root of x plus 2 squared is just x plus 2. And I take away 1, because that's what this says. Look at it. It says take whatever's in here, square it, and take away 1. So I squared whatever's inside here, and I took away 1, so I get x plus 1. For part B, I have g of f of x. So that's equal to, we're doing it the opposite way now, so I have g of x squared minus 1. And g, the rule for g says whatever's here, right, take the square root of it and add 2. Right, all underneath the square root sign. So this is going to be equal to, so you can see it, let's do it right here. So this is going to be equal to the square root. Whatever is here, I just write down here, so x squared minus 1, and then I add 2 to it. And so this is equal to then the square root of x squared plus 1. And you're all done. Be careful. A lot of students will try to take this square root through addition, but that is not a valid operation. Right? Square root does not go through addition or subtraction. It does go through multiplication and division. All right, so now we want to solve for x. All right, so to solve this problem, this is solving what's called an exponential equation. And all you have to do is take out your ln tool, because your ln tool will move down these exponents, and that's the real issue. So here's my equation. So what I'm going to do is I'm going to ln both sides. And if I ln both sides, ln's have the property that I can move the exponents down in front. And so what I get then is x ln of 5 equal to x plus 3 all times ln of e. And ln of e is a nice number of 1, so it's going to go away. And so I get x ln of 5 equal to x plus 3. And I want to solve this for x, so I have x ln 5. So I subtract x from both sides, so minus x is equal to 3. And I'm going to pull out the x, so I have x ln of 5 minus 1 equal to 3. Now be careful here. A lot of times students will say this is ln of 4, but you can't do that. I always tell you guys ln's a car and 5 is its passenger. And the passenger can't get out of the car unless you use one of those rules. We talked about these rules, like when you add logs, it's the same as multiplying, so a times b. If you subtract logs, it's the same as dividing ln of a minus b. Oh, sorry, a divided by b. And then if you have the ln, of course, of a to a power p, the power can come down, so p ln of a. And that's what this is the property we're using here. So this is just ln of 5, and then take away 1. So x is just going to be equal to 3 divided by ln of 5 minus 1. And if I want to figure out what that number is approximately, I can use my calculator and do 3 divided by left parenthesis ln of 5 in parenthesis minus 1 in parenthesis for the bottom. And I get out approximately 4 point, let's do the 2 decimal places, 92. Right, so remember, when you solve an equation, you can always check your answer. I can always just plug 4.9 into for x. And if I do it on this side, I'll get some number. If I do it on this side, I'll get another number, and hopefully these numbers agree. Now, if I round it, it's just going to be approximate. It won't be exact. Okay, so here's another exponential problem. A culture of bacteria doubles every 2 hours, assuming the growth of the bacteria is exponential. How long will it take for the culture of bacteria to triple? So on this, you want to use what's called the exponential model. And we have the amount of bacteria, so let's just say A of t. is equal to the initial amount, a naught, e to the kt. So to review this real fast, remember a couple things. This is the initial. We call this the initial value. It's what you start at. And then this k has a special name. K is called the relative growth or decay rate. In this case, it's growing because it's doubling every 2 hours. So this is the relative, in this case, growth rate. T, of course, is usually time. E is a number, right? 2.718, blah, 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 the natural number. And we use this to model any exponential problem. Or we can use it to model any exponential problem. So how do we use it to model this problem? Well, I know it doubles every 2 hours. So what that means is if I plug in 2 for t, it's going to double. So I get not just a naught back, but 2 times a naught. And I can actually solve this for k because when you divide both sides by a naught, these cancel. And so I have e to the k times 2 equals 2. I want to solve for k, so I'm going to ln both sides. Because ln is this function, this tool, that will bring down exponents. So I can bring down this exponent in front. So I have k times 2. ln of e is equal to ln of 2. And of course, ln of e is 1. And so I'm just going to get k to be equal to ln of 2 all divided by 2. So this gives me some information. Now I know a of t is equal to a naught. I don't know the starting value, but now I know k, so e to the ln of 2 divided by 2 all times t in the exponent. Now it says, how long will it take for the culture of bacteria to triple? So now I'm going to pretend, so I have a naught, that t is the tripling time, so e to the ln of 2 divided by 2, and now t is not a variable anymore. I'm going to pretend t is the actual time it takes to triple. And so if t is the time it takes to triple, I don't have just a naught left. I now have 3 times a naught. And again, a naughts cancel, and I'm going to be left then with this e to the ln of 2 divided by 2, all times t in the exponent equal to 3. To bring down the exponent, I'll ln both sides. When I ln both sides, this expression right here can come down in front. And I get ln of 2 divided by 2 times t, ln of e equals ln of 3. ln of e again is 1, so it's going to drop off. And I can solve this for t. So t is going to equal, since I'm dividing by 2, to move it over I multiply by 2, so 2 times ln of 3. Since I'm multiplying by ln of 2, to move it over I do the inverse, the opposite, so divide by ln of 2. And so that's my time in hours. I can figure out what this is approximately with my calculator if I want to. So let's take my calculator and do 2 ln of 3 divided by ln of 2. And I get about, let's just do about 3 hours, right, to triple. Okay, number 7, I want to solve a trigonometric equation now. So this is a secant of x equals -2. So to solve this one, I don't like to work with secant, so I change it to cosine. So I have 1 over cosine of x is equal to -2. And then I can multiply both sides by cosine of x, get 1 equals -2 cosine of x. And then I can divide both sides by -2 to get cosine of x equals minus 1 over 2. I'm more familiar with solving this type of equation in terms of sines, cosines. And the way that this works, there's a couple tools you need to use. The first tool I'm going to use is the fact that all the trigonometric functions are positive in the first quadrant, only the sine is positive in the second, only the tan is positive in the third, and the cosine is positive in the fourth. So all students take calculus. So what this tells me is that the angle can't lie in the fourth or the first quadrant. So my thetas, whatever my angles are, have to lie in the third and the fourth. And to figure out this little angle, this reference angle from here to here, all I need to do is figure out, which angle, when I take the cosine, gives me 1/2. And again, I use another tool, which is this table. So 0, pi over 6, pi over 4, pi over 3, pi over 2. And then I have cosine of theta, and I have sine of theta. And I just have to remember the cosine of 0 is 1, so this starts off root 4, root 3, root 2, root 1, root 0, and of course they're all divided by 2, divided by 2, divided by 2, divided by 2, and divided by 2. And the sign is exactly the same, but opposite. Square root 0, square root 1, square root 2, square root 3, square root 4, divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. And now I look at this, cosine is equal to 1/2 at pi over 3. So this angle is pi over 3, and this angle down here in blue is pi over 3. These are just the reference angles. And so to find the actual angle, I have to figure out what this is here, which is just pi minus pi over 3. So pi minus pi over 3. I get a common denominator, so I get 2 pi over 3 for the first one. So I know x should be 2 pi over 3, and I can add any multiple of 2 pi, so 2 pi n. And then the other angle occurs right here, so it goes from here all the way around to right there, and so that's pi plus pi over 3. And so I find a common denominator, and this is then 4 pi over 3. And so I get and 4 pi over 3, plus again, any 2 pi, so 2 pi n. Right? N is an integer. So it's, 0, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, and so on. Okay, now I want to use left-hand and right-hand limits to determine the following limit, and use a definition of continuity to explain why the function is or is not continuous at x equals negative 2. So let's look at this. We'll take the limit as x goes to minus 2 from the left of f of x. And then if it's from the left, we use the top piece. And so I'll use this piece here. So I have the limit as x goes to negative 2 from the left of cosine of x. Now cosine is a continuous function, so it's just cosine of negative 2. And then for the next one, let's use green, let's say here. So I have the limit as x goes to 2 from the right of f of x. And instead of using the top, I'll use the bottom, because now here x is to the right of negative 2. And so this is equal to the limit as x goes to 2 from the right of sine x minus 2. And so that's equal to, this is negative. So sorry, that's negative 2. And so this is equal to sine of negative 2. Then we take off 2. And if you check on your calculator, you'll see that these certainly are not equal. And so we can conclude, therefore, the limit as x goes to negative 2 of f of x does not exist, so D and E. Hence, so this is the second part of the question. Use the definition of continuity to explain why this function is not continuous at x equal 2. So hence, I know the limit as x goes to negative 2 of f of x does not exist, so it cannot be equal to the actual value f of negative 2, which is equal to, let's say, cosine of negative 2. Because when you plug in negative 2, you use the top piece. It says less than or equal to. Right, so therefore, f of x is not continuous at x equal negative 2 by definition. Definitions, just definition. Okay, now we come to the limits. evaluating limits with formulas. So when you evaluate limits with formulas, the first idea is simply plug in the point. So like this top one, if you plug in 5, you get pi times 5 plus cosine of 5. And this is a perfectly nice answer. Your calculator will tell you what it is approximately. So this is the limit. Now these other 3, something's going to happen, all right? So I bet you if I plug -1 to this, I get 0 over 0 out, which is an indeterminate form, which means I need to do more work. If I plug 7 into here, I bet I get 0 out, or 0 over 0 out. And I bet if I plug in 1, I get 0 over 0 out. Okay, so let's see, what can I do to these things to find their limit? So in part B, what I might want to do is try to factor the top and the bottom. So the top is done, you can't factor that. But the bottom, I bet you, I can factor x plus or minus something, x plus or minus something. And so I bet it's +1 because that's +1. And it is, and this is going to be then -6. All right, so this times this is, yes, that. And now I can cancel off the x plus 1s. And then this is equal to the limit as x goes to -1 of 1 over x minus 6. If I plug in -1 now, so I reevaluate the limit, I get 1 over -1 minus 6, which is 1 over a -7. So that's my answer, -1/7. Now I can check my answer here by plugging in a number close to -1, like -0.999, and I can plug it into this expression here, this formula, and I should get something close to -1/7. Now C is a little bit trickier. In C, I have a cubic. Now I can factor cubics if I really want to, or I could plug in a number close to 7. You know, since this doesn't tell me, you know, what I should do, maybe I'll just do it. I'll do it the hard way. All right, well, let's remind everybody how to factor x cubed minus 8x squared plus 7 if positive 7 is a root. So how do you divide polynomials, basically? So this is a good review for dividing polynomials. So I want to divide x plus 7 into x cubed minus 8x squared plus 7. Now the idea is you try to figure out how many times is x going to x cubed, and hopefully you say x squared times. And if you do that, I get x cubed plus 7x squared. And then I take these two polynomials here and I subtract. So x cubed minus x cubed, these cancel. Negative x squared minus 7x squared is a negative 15x squared. And I still have plus then 7. And so then I'm going to add 15x, because how many times is x going to negative 15x squared? And I guess I'm going to put a negative 15x there. So let's fix that. So minus 15x. And if I do that, I'm going to get minus 15x squared. And then plus, or I guess minus, and so minus negative 15x times 7. All right, and so that's minus, what's 15 times 7? So I think that's 95x. 15, 70, 105x. Okay, so at this point, I'm thinking something's going wrong. So let's go back, and maybe I don't get out 0 over 0 when I plug in here, and I think that's the case actually. So I assume that if I plugged in 7, I got 0 over 0, but it turns out, yeah, I don't. Right? So I knew something was going wrong there. So let's check this out. So if you plug in 7, take out your calculator, and you plug 7 into the top, right? So I get 7 raised to the 3 minus 8 times 7 raised to the 2, and then plus 7, I get out negative 42. Okay, so this actually is okay. If you plug in 7, on top I'm going to get out 42, and on the bottom I get out 0, which is perfectly fine because it just means this limit does not exist. It either blows up or blows down because you're taking some number 42 and dividing either by a really small number on the right of 0 or a small number on to the left of 0. So it could blow up, it could blow down, and so this limit does not exist. All right, now D, definitely when I plug in 1 I get 0 over 0, so let's change this to D. And so to do D, what you can do is you can make a table. That's one idea I would have for this one because I know I can't do any sort of factoring. So I could plug in a number like 1.001, and I could also plug a number into the left, which may be like 0.99. And I can use my calculator to figure this out. So I could do sine of 1.001 minus 1 in parentheses divided by left parentheses 1.001 minus 1 in parentheses, and I get out about 0.999999999. And you can do it from the other side too. Right? You probably get out a number like 0.9999999. And so you know this answer, the limit, as x goes to 1 of sine of x minus 1 over x minus 1 is equal to 1. All right, make sure you do the other side too on this one. All right, the last two limits are limits as you go to plus or minus infinity. So let's just do part E. Now remember, this turns out to be real simple. I'm going to switch colors here. When you go to infinity, you can always cross off the lower degree term. So here's the highest degree term right here, the cube. So I can cross off the 5x, the 2, the x squared, and I can also on the bottom cross off this x. So what I get is the limit as x goes to minus infinity, so all the way to the left, of negative 4x cubed over x cubed. And again, I can cancel off the x cubes. So this is equal to the limit as x goes to minus infinity of negative 14, which is equal to, now I plug in x equal negative infinity. There's nothing to plug into, so I just get left with a number of negative 14. F is similar. So what I can do on F, I have it going to infinity of 2 minus 3 e to the 2x divided by x minus 7 e to the 3x. Now when I do this, let's change colors here, let's do black. So I can cross off the lower sort of powered terms. E grows so fast that this 2 does not matter. 7 e to 3x goes so fast that doesn't matter. So I get the limit as x goes to infinity of negative 3 e to the 2x divided by negative 7 e to the 3x. And now I can't just cross off e to the 2x divided and e to the 3x because there's going to be stuff left over. So what I can do though is I can get rid of the negative signs because they cancel, and I have 3 over 7, and I have 2 to the x on top and 3 to the x on the bottom. So exponents actually subtract. So 2x minus 3x, so I'm left with an e to the x on the bottom. And so there are several ways to see this. You know, e to the 2x is equal to e to the x times e to the x. And e to the 3x is equal to e to the x times e to the x times e to the x. So if you divide these, you can see 2 of them cancel. I'm left with 1 on the bottom. And if I go to infinity, what happens is I get this 3 over 7 e to the infinity. And remember now, e to the infinity is a huge number, so it's like 3 divided by this huge number, so it's equal to 0. You could check this answer by plugging in a really big number like 100, and for x, you'll see your calculator says 0. You could check negative 14 by plugging in like negative 100 or negative 1,000 maybe for x, and you should get a number close to negative 14 here. Okay, so this last page, it says use a graph of the function below, f of x, to answer the following questions. The function is not continuous at what x value? So remember, a function's continuous as long as you can draw it without lifting up your pen or pencil. And so you're continuous, you're continuous, you're continuous, you're continuous, you're good, you're good, you're good, you're good, you're good, you're good. As soon as you get to x equals 0, you have to jump. And so it's not continuous at x equals 0. And there's one more. So now I'm continuous, but now I have to jump up. So I'm not continuous at x equals 2, but then I'm continuous again. So x equals 0 and x equals 2. Finally, let's answer these limit problems. So what is the limit as x approaches 0 from the right? So let's do this one. So from the right. And so as I approach 0 from the right, so here's 0 as I approach from the right. So I'm coming down here, I approach height -1. So that's -1. Whereas when I approach from the left, so here's the left, I approach height 0. And so for this one, we say this, I'm out of room here on this page, so we say this does not exist as you go to 0. Because from the right it's -1 and from the left it's 0. Since those two values do not agree, we say the limit does not exist. Okay, let's look at this one, the limit as x approaches -2. And if it approaches -2, that's over here. So as you approach -2, this is actually continuous. So, as you come in from the left, it's height 0. As you come in from the right, it's height 0. So I bet you this is equal to 0. Let's do this one. As you go to -infinity, so you say, look all the way out here on the graph, and keep looking, and it approaches this asymptote, which is 2. And so this approaches height 2. On the right, if you look at infinity, it keeps going down, down, down. So we'll say, on the right, it goes to -infinity. Finally, this last limit, as x goes to 2 of f of x, we look, and from the left, it goes to height 1, and from the right, it goes to height 1. Even though it has actual height 2, that does not matter. The limit is still 1. So this is equal to 1. Right? Because the limit from the left is the same as the limit from the right. This sort of captures that subtle nature of what the limit actually is.